RSA is supposed to be one of the most secure crypto algorithms, and it protects everything from bank transactions to medical records. But if it's implemented wrong, you can break it at home with just your laptop. And today, I'm going to show you how. So let's just get started by talking about symmetric encryption. Symmetric encryption is what we had before RSA and other asymmetric encryption schemes became available. And so I'm going to walk you through like how did it work and why do we need asymmetric encryption and why do we need RSA. So in this example here, we're looking at Alice on the left side and Bob on the right side. So Alice has a message. That's that little like text that you can see there. And she has this key. Bob also has that key. With symmetric encryption, the sender and the receiver must both have the key. That's the only way they'll be able to read the message. So what does Alice want to do if she wants to send Bob a message? You can see here I've got two lines in the center of the screen. That line represents some distance between them. So she's physically sending Bob a message. Maybe she's sending this over the internet. Maybe she's mailing it there. You could use RSA there with paper if you really wanted to. How does Alice is going to have to send that message to Bob? So what she's going to do is she's going to take her message and her key and she's going to run it through a symmetric encryption algorithm. And so this is what it looks like. You've got the message here and you can't read the message, that key's blocking it. You need to have the key if you want to be able to read the message. And then she sends that over to Bob, shoots it all the way to Bob. So Bob now has this encrypted message, and because he already has the key, he can combine the encrypted message with the key using the decryption function and get back the plain text. This should be pretty straightforward. Most people probably know how this works. You know, if you ever like encrypted a Word doc, or what else do you encrypt? PDFs. It's using symmetric encryption. That key is your password. And the only way that someone will be able to decrypt your message is if they have a key. Now this poses a problem. Well, let's just say that Alice and Bob are not physically close to each other. They're on the other side of the world and they're communicating over the internet. And they want to make sure that no one can read their messages. If Alice wants to talk to Bob, she has to send her messages to her ISP. So maybe she's using Verizon. She sends it to Verizon. That gets sent to CenturyLink, and then that gets sent to Time Warner. Like that message is going through multiple different entities before it finally makes its way to Bob. And any person along the way can see what is being sent. And so it's really important that this gets encrypted. Now, if Bob needs the key to read what Alice sends when she encrypts it, how the heck does Bob get the key in the first place, right? If Alice tries to send the key to Bob, then anyone who can see those messages can just take the key. Then when Alice sends the encrypted message, decrypt it. She needs to be able to send Bob the key in a way that no one else can see it. And this is a huge problem with when the internet was starting, because how do you have encrypted communications in a scalable way if you have to like physically give someone the password, right? Like you have to go up to their ear and tell them the password, or you have to like put the password on a flash drive and then like mail it to mail the flash drive. But what if someone opens your package? Really not a good solution to that problem. So that's why we have asymmetric encryption, and that's why RSA was created. So let's talk about asymmetric encryption. It's a little bit more complicated, so before I move into the animations, I'm just going to talk through what we're seeing right now. The key thing with asymmetric encryption is that instead of having one key that both people use, we actually now have 4 keys. So you can see these 4 keys. I try to distinguish it here. Bob's keys are pointing to the top right, and Alice's keys are pointing down to the bottom left. Okay, and they're also labeled. Each person has a public key and a private key. So the public key is something where you can share that key publicly. That's why it's called the public key, and that's perfectly safe. So Alice can share her public key to the world, and that's perfectly safe. And she uses her private key to decrypt any messages. So what will happen is that if she wants to send a message to Bob, Bob will take Alice's public key, encrypt the message using that public key, send it to Alice, and then Alice will not use the public key to decrypt the message. She will use her private key to decrypt the message. I'm going to show you an example where we do the other way around. Alice is going to send a message to Bob using Bob's public key. The important thing to know here is that these keys are paired. So Alice can only decrypt messages using her private key that are encrypted using her public key. So if someone wants to send a message, they need to use the recipient's public key, and then the recipient will be able to decrypt that message. So if that doesn't make sense, no problem. We're going to actually show you how that works. So Alice is over here on the left. She has her message. That's the text file over here. And she wants to send her message to Bob. Now, in between, again, these two lines, that's representing the internet. So Alice is sharing her public key to the world, and Bob is sharing the public key to the world. That's perfectly safe. That's perfectly fine. That is intended. Alice and Bob do not want to share their private keys, because if they share their private keys, then that means anyone else with that private key can read their messages. Another thing to note as well, I'm showing here 4 keys. The 2 keys that Alice has are not going to be used in this example. Alice will have her own keys so that if Bob wants to send her a message in the future, Bob will use Alice's key to send that message. So when Alice is sending a message to Bob, she only uses Bob's public key. So she uses Bob's public key, she grabs that from the internet, she now has Bob's public key. She takes the message that she has, and she has the key, and she uses it to encrypt the message. So now Alice has an encrypted message that uses Bob's public key. Now she can send this over the internet. So she sends this over the internet, she sends it to Bob. Bob now has a message that's encrypted using his public key, and only his private key, this blue key, that's the only one that can decrypt it. And so he uses his private key and he decrypts the message. Now this is pretty crazy because it means that Alice and Bob do not need to share any sensitive information for them to communicate. Bob needs to advertise his public key to the world, and then anyone who wants to send him a message goes and gets his public key, and they can send him a message. So in this paradigm, in this model, it's perfectly safe to send those public keys out there. I just want to heavily reinforce that again. Those public keys are supposed to be out there. Actually, you're supposed to advertise your public keys on websites where you can identify yourself personally. So some people will like put their public keys on Twitter. I think there's a bunch of other sites that actually store profiles with public keys, because when Alice wants to send a message to Bob, the real important thing here is that she is sending it to Bob and not someone that she thinks is Bob. So if she is online and she's trying to send a message to Bob, but Charlie is pretending to be Bob, and Charlie says, "Hi, I'm Bob, here's my public key." And Alice says, "Okay," and she sends Charlie a message thinking that it was Bob. Well, Charlie can read that message. So this actually shows that it doesn't perfectly solve the problem of accidentally having your messages sent, but it eliminates the problem of how do I share a key, how do I share a password with someone over an insecure medium, and replaces it with this easier problem of how do I know that the person who gave me their public key is actually them. It's a different problem. It's an easier problem to solve. So how does RSA work? It looks a little complicated. I'm going to explain this out as simply as I can. But we're going to see some examples which will explain it even better. So Bob wanted Bob's key over here is what Alice used to send the message. So I'm going to show you the process of Bob generating his public and private key. The oversimplification of how RSA works is that Bob is going to generate two random prime numbers. These are supposed to be two very large prime numbers, and I'll explain why they should be large. But he's going to generate two prime numbers, and we're going to call them P and Q. And then we're going to generate three additional values based on P and Q. So we're going to have N, which is P times Q. Very simple. And then we're going to have E and D. Now, there is some really complicated math here that I don't really feel like explaining. But basically, all you know is that like P and Q go into some magic function, and then E and D come out. Again, these are actually numbers, like the number 7. You can literally replace this with like P put in 7, Q put in 8. Well, I guess 8's not a prime number. Put in 5. You can put in actual numbers for these. These are really just numbers. And basically, we have all of these 5 letters here, which make up the public key and the private key. So Bob's public key is N and E, and his private key is D, P, and Q. That's a simplification of it. So if you have the letters N and E, you have Bob's public key. If you have the letters D, P, and Q, you have Bob's private key. And then if you take the public key and then you encrypt a message using the public key, that encrypted message is called C. Don't worry if you didn't track all that, I'm going to explain it again. But let's actually look into the additional details here. So I'm going to put in some values so this isn't so theoretical anymore. And I'm just hiding right now how we generated these values. That part doesn't matter. The part that matters is that you know that the private key is D, P, and Q, and the public key is N and E, and the encrypted message is called C. So when a message is sent using RSA, you are going to get over the internet, right? So if someone was listening between Alice sending that message to Bob, this is what they would see. They would see the C value, right? This 996.894.379. That is the encrypted message that Alice sent to Bob. That is the ciphertext. That's why I'm using the letter C. And an attacker would also have N and E. Why? Because Bob's public key is N and E. So Bob is publicly advertising to the world, here's my public key, here's my N, and here's my E. And so when Alice sends Bob a message, an attacker will be able to obtain N, E, and C, these values. This is 100% intended in the threat model of RSA. All of that information is meant to be public. Now, here's where the vulnerability comes in. I mentioned on the previous slide that P and Q should be large prime numbers. There's a very good reason for that. And the reason is that if P and Q are not large numbers, it actually becomes easy for an attacker to guess what P and Q might be. And if they can guess what P and Q might be, well, they'll be able to get the private key when they get D, and I'm going to show you how they get D. So right now, when the message is sent publicly, we've got N and E. All right. So I said N is P times Q. So from Bob's public key, you can get P and Q by just factorizing the value of N. So N is going to be P times Q. If you go plug that into a factorization tool, you will be able to spit out two possible prime numbers that will multiply together to get N. So if you factorize N, the resulting values that you get are possibilities for P and Q. All right. Now the next step here, once we get P and Q, is to get D. This math is a little bit more complicated, but basically all you need to know is that there's a formula that you can plug in. And what does the formula use to get D? To get D, we need P, Q, and E. If you notice, we happen to have all of those values. N and E are the public key, and then, so we have the E there, and then the P and Q, we're gonna guess what P and Q are by factorizing N. So if N is a small number, the number of possible factors should be small, which means that you should be able to quickly guess all the possible values of P and Q and derive possible values for D, and then try to decrypt the message. Because once you have D, P, and Q, that's the private key, you can now decrypt the message. So the reason, again, why P and Q should be large prime numbers is because it makes it harder for an attacker to guess what P and Q are. If the attacker can guess what P and Q are, then the jig is up. Everything is broken. And that's why in real RSA, or in proper implementations of RSA, those P and Q values are very, very, very large. In the example I'm going to show you today, it's going to be an example of someone implementing RSA poorly. And you can see here that N is 1,079. That is not a particularly large number. So two numbers multiplied together is 1,079. There are not very many possibilities for a combination of two prime numbers that can multiply together and become N. And that's how we're going to decrypt the message. So now we've got all of the values. We basically have Bob's private key. We can decrypt the message. So let me just recap the steps that we have here. Step number 1, you're going to factor N to obtain P and Q. Once you obtain P and Q, you can calculate D. I actually suppose you could do these at the same time, but you're going to factor N, obtain P and Q, calculate D using the E value, and then you're just going to keep plugging those values in until eventually you're able to decrypt the message. So if you want to write these numbers down at home, I'm not showing you the whole decrypted message because I don't want to give you any spoilers, but the value of N over here, we have 1,079. The value of E is 43. If you don't want to copy all of C, you can just copy like the first like 3 numbers. So 996, 894, 379. You can just copy those 3 values, and then you'll just decrypt the first 3 letters of the message instead of the entirety of it. It'll make it a little bit easier on yourself if you want to do it that way. And what I'm doing as well is showing you my work here that at the end of what I'm going to show you, we're going to have P, which is going to be 83, Q, which is going to be 13, D is going to be 595. And then now that we've got P, Q, and D, going back to the previous slide, P, Q, and D is everything we need for the private key. Now we can decrypt the message. So let's get cracking. I want to show the demo, but let me go and double check and make sure that we've got no questions in the chat right now. Only question in the chat right now is, shouldn't there be a buffer I assume you mean in between the in the encryption? Yes, there should, in a proper implementation, be a buffer that would make it harder for an attacker to kind of be able to brute force the values. All right, cool. Now let's go and show you all the demo. This is my favorite time of these sessions, actually going and breaking stuff. So I've got my Kali box over here, and I'm in my demo folder, and right now I've got this message.txt. This is what I showed you on the slides. It's the N value, the E value, and the C value. That is the information that as a hacker could obtain if they were listening to communication. So again, N and E are values from the public key. So if Bob is receiving a message and someone is intercepting the message that he's receiving, they would get N and E from the public key that he broadcasted to the world, and they will get C from the actual message that was being sent to Bob. Those are the three values that we have. Those are the three values that an attacker would obtain. And I mentioned the first step that we're going to do is factoring. So I'm just going to go online and I'm going to just Google for a factorization calculator. And please disregard my spelling. And let's see, we got a factoring calculator from Math Papa. All right. No, that's not what we want. We want a factorization calculator, or factor calculator. What am I looking for? Prime factorization calculator. That's what we want. All right. Prime factorization calculator. And what we are going to do is we're going to put in our n value. So that's 1079. And I'm going to hit calculate and see what we get. Only one match. So again, this is why you need a very, very large prime number, two prime numbers when you're calculating n, because right now we only have 13 and 83. Now, let me show you what happens if you do have two large prime numbers. So if I go and I search for large prime numbers, we're going real simple here. Like if we just get a list of prime numbers on Wikipedia, and you know, let me choose my favorite prime number here. So I'm gonna say none of these are exciting enough. All right, that's an exciting prime. So if I do this prime number times this prime number, I really hope these are prime numbers and I'm not getting my leg pulled by Wikipedia. All right, number's too big. We went too big. We need a smaller prime number. Let's do 991 and 997. 991 times 997. That's a bigger number. And so if we do factorization on this number, we're going to get more than one option, I would assume. Nope, only one option. All right. Then you really want to make sure that you choose large prime numbers. Normally in RSA, these values that you choose are going to be like the massive numbers where when you multiply them together, Google's going to tell you the number's too large to display on the screen. So we have 13 and 83. I'm going to go over here and I'm going to open a Python file. Now I cheated a little bit. I set this up in advance. So I have a decrypt.py file and I filled in most of the information. I filled in everything except for P and Q. So what we need to do is put in those P and Q values. 13 and 83. 13 and 83. And let me just show you all that, where the rest of the values came from. And I'm going to close out of Firefox because this ad for food is making me hungry. So we got P and Q from N. N is N, we went online, we factored it, and we got these two prime numbers. That's P and Q. E is E, that's copied and pasted. And then again, N is equal to P times Q. Now C is the ciphertext. So I just took this message here and I just made it into an array and just split up all the values like that. And then there is some slight math here. So I didn't feel like implementing all of the math required to solve this. So I'm using Gimpy, or GMPY. GMPY2, it's a Python library that you can download for free. So if you go online, you go and search it up. I don't know why it's called GMPY. I don't know if you're supposed to pronounce it Gimpy. I'm just going to call it that because why else would you name your project GMPY? And then we're going to need to calculate, we're going to have to do like 3 equations here. One is we need to calculate, is this phi or phi? Which is just P minus 1 times Q minus 1. That's simple enough. And then we have D, D is that, and D is the inverse or inverting E and phi. So remember on the slides, I showed like a gear that generated two numbers, and I didn't give any explanation other than it's a gear that generates two numbers. Yeah, that's what this is. One of those values is being derived from this equation, and the other one is from this equation. Uh, you do not want to memorize this. I googled for these values on Stack Overflow. Like I found them on Stack Overflow. Legit copied and pasted them into my Python script here to actually get the values that I need. And then to actually decrypt the message, what we're going to do is we're going to go through every single value in the array, one character at a time, and we're just going to decrypt one character at a time. That's what this for loop is. And then the decrypted value is going to be another math equation. So we're going to do the power function, and we're going to pass in I, which is the index in the array, D, which is this value that we just obtained by using GMPy, and N, which is P times Q. If you need to pause and like write all this down, feel free to do that. Take a screenshot. This isn't going anywhere. But this is a very, very simple script. It looks like a lot, but like 2/3 of this script is just like the values that I copied from the message that we were given, the encrypted message. The only real like code here is just this section here where we calculate this phi value, we calculate D using this invert function, and then we calculate the decrypted message M with the power function in Python. And so, well, now that I've walked you through the script, we're just going to run Python 3 with the decrypt function, and bam, this is our message. Now, the message, when I had it print out, it prints out every single character on a new line, which is why it's all spread out like that. But we've just decrypted a message. So we didn't even need like password crackers or ASICs or like anything to actually be able to break this RSA encryption. I literally went on Google, found a website that was riddled with ads, factored my prime numbers, and bam, I got my decrypted message. Now, we got lucky. I tried to show an example where maybe you wouldn't try to factor it and just get only two possibilities. In reality, when you try to factor it, if RSA is being implemented properly, you're gonna get a lot more than like one pair of possible values for P and Q. You're gonna get millions of possibilities, or billions of possibilities, or trillions of possibilities for what they could be. So that's what would happen in reality. And instead of me being able to just like say, oh yeah, there's only one possible combination, let me just plug this in here and solve it right away, you would have to write a program which would just guess all those combinations, right? Because if we tried to run this program and we got P and Q incorrect, so let me just show you what that might look like. So what if we said, P and Q, so I guess 1 times 1079 is 1079. So that math still works together, but those are the wrong P and Q values. If I run this now, we get an error. It doesn't work. So you definitely need to have the right values. Or if I just, put in whatever values, I feel like it didn't work, right? It didn't decrypt the message properly. So that's the important lesson here. That RSA is extremely secure. I don't want to give everyone the impression like, wow, like I can crack RSA with a Google search and like a 30-line script. Most people are not implementing RSA in this way. There are a lot of libs out there that implement RSA properly, and you should not really run into this problem in the real world. However, if you happen to be responsible for implementing an RSA algorithm for some reason, make sure that you are choosing large prime numbers, because you want an attacker to not have one option to guess as to what P and Q are. You want an attacker to have billions or trillions of possibilities for what those values can be. So I hope that was informative. Stay subscribed for future episodes, and I hope to see you again. Please, if you have additional recommendations for topics that we should cover in the future, if you're watching this on YouTube, leave those in the comments. We keep looking at them on a regular basis, and we choose topics for future episodes based on those comments. Thank you very much, everyone.